Get started whenever you're ready. Thanks.
Hi, I'm Rishi Malatkar. I'm a senior.
Hi, I'm Akil. I'm a senior.
Hi, I'm Vishnu. I'm also a senior.
Hi, I'm Varun. I'm also a senior.
So we're team 19232 from Arizona College Prep High School, and today we're going to be talking about the rise of online gambling, what's at stake. To understand why this issue matters today, we start with the shift that changed the United States sports betting scene. For years, it's been federally restricted, but after the 2018 Supreme Court decision that removed that barrier, the legalization has spread rapidly. By 2025, the U.S. sports betting platforms have generated over $15 billion in revenue from $150 billion in wagers, and 22% of Americans have online betting accounts. But that growth comes with consequences. Illegal betting scandals have raised concerns about sports integrity. A bet that once required effort can now happen in seconds, increasing risk of problem gambling, reduced savings, and debt. Bringing us to the central question that the M3 challenge has posed to us. Should society be concerned about online gambling and its continued growth?
So before constructing our models, we established a few assumptions that stay consistent across the entirety of our solution. First, we define disposable income as gross income minus essential expenses, including taxes, housing, food, healthcare, transportation, and debt service. Second, we use the legal gambling ages of 21 in the United States and 18 in the United Kingdom, so underage individuals are excluded from participation models. Third, we isolate sports betting from other gambling activities like casinos and lotteries, so the model stays focused on the behavior we are actually studying. And fourth, we assume relatively stable short-term economic conditions, meaning inflation, wages, and employment do not shift dramatically during the time horizon of the model.
Beginning with question 1, playing with house money, the goal is to estimate a person's disposable income based on salary, age, and other demographic factors. This is our team's equation to derive the individual's disposable income, or D, which is equivalent to the gross salary subtracted by taxes, housing, food, healthcare, transportation, and other essentials such as utilities, insurance, etc. Each of these cost components are their own submodels calibrated against public data, and the inputs to these submodels are salary, age, region, household size, and filing status. 5 demographic variables that we found together capture the dominant sources of variation in American household budgets. The tax components combines federal income tax, FICA taxes, and regional, state, and local taxes. We use a 2024 IRS regional marginal brackets for federal taxes, added 6.2% for Social Security and 1.5% for Medicare through FICA, and then estimated regional tax rates using population-weighted averages. Weighting state rates by population better reflected where people in the region actually live rather than treating each state equally. For housing, we use a piecewise model. Below the regional median income, housing follows the 30% HUD affordability guideline, while above the median, housing increases more slowly at 15% of additional income because higher income households usually spend a smaller share on housing. We then applied regional multipliers to reflect cost differences from 0.85 in the Midwest to 1.3 in the West. For healthcare, we started with a $2,400 base premium for employer-sponsored insurance, then added an age-based term with a 1.3 exponent, which was derived from medical expenditure panel survey patterns, and was important because healthcare costs rise systematically with age, reducing disposable income for older individuals. Here are results across 8 representative profiles spanning ages, salaries, and regions. The key pattern is that the percentages alone can be misleading, as a $25,000 earner keeps almost $6,000, while the $150,000 earner keeps almost $36,000, which equate to around 30% of their gross income. But the higher earner has far more flexibility, which matters when evaluating gambling exposure. To test the robustness of our model, we changed each parameter by 10% around our baseline profile. A 30-year-old single male with a $55,000 salary in the Midwest. And based off our data, we learned that salary and housing not only had the biggest effect, but that the model is sensitive in the right places and that gambling exposure should depend on earning power, and cost of living, which is exactly what our sensitivity test showed. So the strength of our model is that it was able to capture nonlinear costs, especially housing using income and healthcare through age, and it is modular so the tax, housing, food, and healthcare inputs can be updated separately. And since it's demographically sensitive, the salary and region, salary, age, region, household size, and filing status can be adjusted as well. However, the weaknesses come from the oversimplification, as we do assume employer-sponsored health coverage, which not all of them have, and we don't fully capture debt, investment income, or transfer payments. And we do use regional averages, which can hide local differences from cities like New York City to a town in rural Pennsylvania.
Q2 is Know the Spread. The goal is to predict how much an individual will gain or lose through online sports gambling over 1 year based on their demographics and risk tolerance. 5 assumptions drive our model. First, an individual's probability of having a betting account depends on their age, gender, and country. Second, active bettors wager a fraction of their disposable income, with the fraction depending on risk tolerance, which can be either conservative, moderate, or aggressive. Third, bettors place different types of bets like straight bets, parlays, and proposition bets, with the mix shifting based on risk tolerance. Fourth, the sportsbook built-in margin averages 4.5% on straight bets and 15 to 30% on parlays. And fifth, each bet outcome follows a Bernoulli distribution with win probabilities derived from the implied odds minus the sportsbook's fee. This table lists all the variables in our Q2 model. The key ones to know from this table are D, which is disposable income from Rishi's part Q1, Rho, our risk tolerance slider from 0 to 1, and G at the bottom of this table, which is the annual net gain or loss, which is our final output, as you can see here. Now, our risk tolerance parameter Rho controls 3 things simultaneously. First, it controls the value of what people bet. The formula W equals 0.05D plus 0.75 Rho means a conservative bettor wagers just 5% of disposable income, while an aggressive one could wager up to 80% of their disposable income. Second, it controls how often a person bets. The formula N equals 50 plus 550 Rho gives conservative bettors about 50 to 120 bets for years, while for aggressive bettors, they could place up to 300 to 600 bets per year. And third, it controls what type of bets these people make. Conservative bettors stick mostly to straight bets at 75%, while aggressive bettors shift heavily toward parlays at 45%. And as we'll see next, that's where the sportsbooks takes the biggest fee. Now let's see what happens on each individual bet. This formula says every bet has 2 outcomes. You win and get paid W times the payout odds, or you completely lose your wager. On the left with straight bets, the green line shows a 50% true win probability, with the payout being even money at 1x and the house edge in red just being 4.5%. Now follow what happens as we move to parlays. The blue payout line shoots up 2.6x for a 2-leg parlay and 6x for a 3-leg, which looks great, but the green win probability drops to 25%, then 12.5% for a 3-leg parlay, and the red house edge climbs from 4.5% all the way to 25%. Now for a Monte Carlo simulation, the formula says G equals the sum of all individual bet outcomes over a year, which is where we add up every win and loss to get the total annual result. The first step of this is calculating basic setup values like the average wager and the number of bets from our formulas. The outer loop runs 10,000 times, which is supposed to simulate 10,000 years. For each year, the inner loop goes through every bet, and it generates one random number to pick the type of bet, which can be the straight, the 2 types of parlays, or a proposition bet. Then it generates a second random number to determine whether you win or lose that bet. Wins get added to the net function, and losses get subtracted from the net function. And after 10,000 simulated years, we have a full distribution of outcomes where we can analyze a mean, median, standard deviation, and certain percentiles. Now here are results from that. 3 things mainly jump out from this. First, losses grow with both income and risk level. The 55K earner goes from a $650 mean loss as conservative to over $4,300 as aggressive. Second, the orange standard deviation bars are almost as large as the blue mean bars for aggressive bettors, which shows how inherently random and unpredictable gambling outcomes can be. Third, the 55K aggressive bettor has a 5% chance of losing over $11,600, while the 25K aggressive bettor could lose nearly $4,800, which is over 82% of that person's entire disposable income. Now for a sensitivity analysis, we tested 2 key parameters. On the left, we have our house edge. We found that by increasing 2 percentage points for house edge, we caused losses to jump 35 to 40%, while decreasing it by 1% caused losses to fall 18 to 22%. And on the right, for our bet mix, we found that shifting just 10% of bets from straight bets to parlays increased losses by 12%. And for our strengths and weaknesses, our biggest strength was our Monte Carlo approach with 10,000 simulations giving us the full range of outcomes. And another big strength that we had was that we had a 215 predicted mean annual loss on average per account, while 205 was the real, which is within 5% of each other. And then for our weaknesses, we didn't capture loss chasing. And we also treated all bets as independent, whereas some bettors might exploit correlations.
Next, for Q3, we focus on making the financial impact of sports gambling easy for the public to understand. The main question here was not just how much people lose, but how much these losses matter based on the money they actually have available. Our Q3 model takes the outputs from Q1 and Q2 and turns them into 3 measures. The financial impact index shows gambling loss as a percent of disposable income, savings erosion shows how much future wealth is lost over time, and at-risk population estimates how many gamblers cross dangerous thresholds. So Q1 tells us what people can afford, Q tells us what they lose, and Q3 tells us why it matters. For assumptions, we use 10% of disposable income as our financial distress threshold. We also assume 60% of gambling losses would have gone to savings and 40% to other spending. For the long-term model, we use a 4% real return rate. And for population estimates, we applied our Q2 participation rates to the US adult population. These are the main variables and parameters for Q3. The key ones are annual gambling loss from Q2, disposable income from Q1, the savings rate, the investment return rate, and the savings deficit over time. Together, they connect yearly gambling losses to longer-term financial harm. Next, we have the financial impact index. It's one of our main measures of financial impact. Instead of just looking at dollars lost, it divides gambling loss by disposable income. This matters because a $1,000 loss is much more damaging to someone with low disposable income than to someone with the higher cushion. For comparison, a moderate sports gambler in our model loses about $1,820 per year, or about 10% of their disposable income. An aggressive sports gambler loses about $4,310 per year, or almost 24%. Next, we have our erosion model. We assume 60% of gambling losses will otherwise be saved and invested at a 4% real return. For a moderate bettor earning $55,000, this created a 20-year savings deficit of over $32,000. For an aggressive bettor at the same income level, the 20-year deficit is over $77,000. So the main takeaway we see here is that repeated gambling losses are not just short-term entertainment costs, but over time they can be serious lost wealth.
So far, our Q3 model has shown how gambling losses affect individuals, and the next question is how widespread that risk is across the gambling population. Here, we estimate how many active gamblers exceed financial distress thresholds using FII. The left side shows that a meaningful share of gamblers lose more than 5, 10, or 20% of their disposable income. The right side shows that this burden is highly uneven across income groups. For moderate bettors, the burden is above that line in the bottom income quintile and far below it in the top quintile. The takeaway is that millions are at risk, and lower income gamblers carry a much larger share of the burden. We also tested how much this conclusion depends on key assumptions. Lowering the savings substitution rate reduces the long-term savings deficit, but it does not affect the at-risk population, since that depends on FII rather than savings behavior. The distress threshold has a much larger effect on the population estimate because it directly changes who counts as financially at risk. So the exact count changes, but the main conclusion does not. Under all reasonable assumptions we tested, the affected population still remains in the millions. One strength of Q3 is that it uses 3 lenses of harm: current burden, long-term erosion, and population level risk. It also captures the regressive pattern directly, which raw dollar losses alone would miss. At the same time, Q3 depends on assumptions. The savings substitution rate is uncertain. It inherits uncertainty from Q1 and Q2, and it focuses only on financial harm. So our defense is not that the model is perfectly precise, but it is that the same broad pattern keeps appearing even when assumptions vary. Our conclusion is that society should be concerned about online gambling, though the risk is not uniform across groups. For some higher income individuals with moderate habits, gambling may act more like a discretionary entertainment expense. For lower income groups, younger people, and aggressive bettors, the harm is much more serious and can build over time. The most important result is that the losses are aggressive, meaning the people with the least disposable income lose the largest share of what they can afford. And here we outline some policies based on our findings from the model. And our main message is that online sports gambling is likely here to stay, but that its harmful effects should be vulnerable, have vulnerable effects on populations, on certain populations. Thank you.
Great, thank you. Any of you guys want to kick us off? Yeah, go for it.
Thank you very much. So, of course, this was focused on online gambling, and you made it very clear, maybe in your second slide or third slide, that you're not considering the lottery or casinos or other ways, other means that people gamble. And I'm wondering whether you've thought of what you do different in this whole process, or what would you need if you were to pursue the other types of gambling? Is that possible?
So you're asking like what other like information and stuff we would need
Yeah.
if
right?
we wanted to go more into like casinos and
Right, because, I mean, gambling has gone on for,
yeah.
a
that's
long,
right.
long time,
Uh-huh.
right? But online gambling is only, I don't know, last
Uh-huh.
small number of years. So if you wanted to analyze and ask similar questions, have you thought about what that would look like?
So obviously the like betting types are a lot different when compared to like sports betting because it in casinos you don't have like parlays or that type of stuff. So we would have to do research on how exactly the house percentages in casinos and how exactly those work over the different type of gambling methods you have there based off the different games, I guess.
There's also a lot of similarities if we want to do, say, casino betting in sports gambling. So some are like, say, salary. If you're trying to analyze different demographics, you would take the same salary. So that's like one big similarity you would use if you want to analyze casino betting. But obviously, like Rishi said, there's differences between how much people gamble in casinos, whether it's on sports or casinos. So that's one big factor of how frequently they bet and how much they bet.
Just a comment, because maybe it's what Dr. Weeks is getting at a little bit, and it's a comment that applies to all teams. I think part of the reason it's curious to ask about the other types of gambling is to put the magnitudes in perspective. Like, you gave some hard numbers for what you think losses would be from online sports gambling, but it'd be nice to know how that relates to, say, like, what people lose to the lottery or casinos every year. You don't need to answer that. I'm just making a comment. Yeah, sorry. If you guys have other questions, go ahead.
Yes, I do have a question, a very detailed, small question. In your question one, you model healthcare component. Can you scroll back to that slide? That was probably one of the first ones. The next one. Yes, so could you tell me more about how did you come up? Well, I think I got 2,400. This is like the base
Yeah.
cost
Yeah.
is it per year?
Yes, that's
Okay,
correct.
then why 18? What is 25 and 1.3? How did you come up with those values?
Yeah, so for the 25,
Lowest.
we noticed that like the healthcare costs are pretty much relatively stable till that point. So there was like there was significant changes after somebody crossed that period. So that's why we have that number. And then the 18 there was like a scaling parameter because we had data from the the medical expenditure panel survey showing like the baseline costs at 25 to 65. So we took the 2,400 and that 1.3 exponent you see there, since the increase is non-linear, that's that's the exponent we got that was calibrated to kind of match the points of the increase. And so that 18 is kind of just like a number that we derived to match the values. I believe at like 25, the cost would be like 2,500, and at 65 would be approximately 5,600. So based off those values, this was kind of like a scaling parameter.
So it is a mix of parameters that were given in the survey and then guess and
Yeah, that's
trial and
yeah,
error,
yeah,
basically.
exactly.
Well,
Yeah.
that 18 and 1.3. Okay.
Yeah.
Okay.
I actually had a question about this slide as well. Are you done?
I'm done. Yeah.
So on your housing component, it looks like your beta for the regional,
The multiplier?
yeah, the multiplier, is that counted twice? Because it's on the inside and the outside of your min.
Oh, yeah, that's actually, it's actually, yeah, supposed to count once, but yeah, that's, it's counted once. Yeah, yeah, it's counted once.
So it's a type. It's a typo, maybe.
Yeah, yeah, it's a typo.
Wait, so I didn't quite follow your answer to the previous question. Like, I get that you chose 18 and 1.3, so this is 2,400 at 25, and then you're targeting to get it to be like 5,600 at 65. But there are multiple choices of the prefactor and the exponent that could lead you to the same number at 65. Right, I could have a smaller, I could reduce 18, I could increase the exponent and also match those 2 points.
Yeah, so we kind of wanted to model the MEPS, the increase based off that they had. So it was kind of like exponential, the increase. So 1.3 was like the exponent that we got to that point with when we had the parentheses around the like the age and then the 25. That's kind of what we had, and that's.
What do you mean? Can you use more concrete words? Like, what do you mean we got or we had? Like, it was a number you looked up, or you cut it from data, or?
Oh yeah, we got from data.
So they gave the 1.3, or you fit data?
No, we calculated the 1.3 based off the points that they had at each age. We kind of tried to model that, and that's how we got 1.3.
Okay. I think I'm good on questions. Are we? Okay. Oh, you have one? Yeah, go ahead. Yeah.
Yeah, so this is on question 2. In terms of your simulation, the number of bets in your code looks like you're using a uniform distribution. Where you calculate the number of bets that take place by an individual?
Yeah.
Okay, could you comment on why you chose that, or and how you got the bounds on that?
Or how we got the formula 50 plus 550 rho. Well, we made it like a linear interpolation. So 50 was like the minimum that we found from our research. So that was like the y-intercept. And then our maximum that we found was 600. So to get even scaling, we made our slope 550. That was just a basic linear formula that we did.
And then in terms of the simulation itself, how did you figure out the distribution for the numbers of people?
What do you mean? Like,
So how do you know the number of people in each demographic?
oh, the number of people from each, that was given by the Siena Research Institute. So from data that we got from one of our sources.
Okay, so you just use the proportions from the.
Yeah.
Okay.
There's like one additional layer to that is you did also have to choose the proportions for like high risk, low risk, and medium risk bettors. So did that come from data? And also, how did you get the mix? The way you upped someone's risk is you made them make more parlay bets, if I understood.
Yeah.
Where did all those numbers come from?
So that was from like the bet params. So like, and then the straight probabilities, parlay probabilities, and parlay. That was like, these are kind of like the implied odds. So the true probability is supposed to be 50%, but then after accounting for the sportsbook's fee, it became 47.6%. But then the like actual like number of bets came from like rho. So 50 plus 550 rho is the formula for number of bets. So that's where the risk tolerance slider comes in. So plugging in any value from 0 to 1 gives you the number of bet value, if that makes sense.
Okay. but there's some mix, like, maybe these aren't the exact numbers, which is like the percentage of, you take the lowest risk person, they have some percentage of straight bet, some percentage of parlay 2, some percentage of parlay 3. Where did that mix of those 4 numbers you need come from?
Oh, yeah, I think the screenshot on the very right is what you're referring to, if I'm not mistaken.
Yeah, I think so, yeah.
These are the,
Yeah. Oh, so it's only 3 numbers. I
Yeah,
guess,
so these
yeah.
are formulas that we derived that help us find the bet mix depending on row.
Sure, but like where does the 0.75 or 0.35 or 0.4 like all come from?
These are like, from our research and the sources that we extracted, we got these numbers.
Okay, sounds good.
Yeah.
Thank you. Okay, I think we're all set.
Okay.
We have 1 minute for you guys to say any thank yous if you would like to, and then we're gonna wrap up.
We just want to thank everybody here at SIAM Math Modeling. Math Modeling, Jane Street, for having us here and giving us this opportunity. Also, our coach, Mr. Thompson, who unfortunately couldn't make it today. He was really helpful with this, and he was a great mentor to have. We want to also thank like our family and friends, I guess, for like supporting us with this and encouraging us to participate in this, because like as seniors in our like second semester, we're not really the most like motivated. I don't know about others, but I can say that about us. So like our parents like it was actually like my cousin who told us about this competition. So I just want to thank him for telling us about this as well. And yeah, just all like the fellow competitors and everybody. It's been like nice talking to them. So it's been a great learning experience. So